Hello everyone, today we will solve a mathematical problem about the quasi-likelihood. First of all, when we have a likelihood, why we need quasi-likelihood? See, in Emily, you face a lot of the time the likelihood, because here we use the likelihood like this, f of xi parameter theta. So whenever we use the likelihood, we need the PDF. And when there is a PDF, there is a fixed parameters. And when there is a fixed parameters, the distribution, specifically the probability distribution, is a specific, like exponential, like gamma, etc. What if we doesn't have any specific distribution? What if we doesn't have a specific parameters? What if we doesn't have any kind of a PDF? If we doesn't have any kind of a PDF, we will not able to find out the likelihood. Then what in this situation, what we will do? We will use the quasi-likelihood, because quasi-likelihood doesn't need the PDF. It only takes two things, mean and the variance. See, this data y1, y2 up to yn, suppose this is a sample observations, and this sample observation does not follow any specific distribution, so it doesn't have any kind of a PDF. But this observation has a mean. It had a mean, it had a variance. So only using these two information and the logic of quasi-likelihood, we can able to find out the likelihood, one kind of a likelihood which is known as quasi-likelihood, and it is approximately with concern with the properties, approximately with the likelihood used in Emily. So we will see using this example. See, we had mean and the variance. It is coincidence that the mean variance equal, and you can think as this is a Poisson. First, whenever you just going to perform quasi-likelihood, only information you need this. You think that you doesn't know what kind of a distribution it is, and you can say that, yeah, I can know that because mean and the variance are same and it is lambda. See, there is a lot of distribution where mean and the variance are same, so it doesn't mean that it is Poisson. And later other examples, you will be very much clear about this. So for quasi-likelihood, we need this mean and the variance. See, mean, here this is the mean given, so we need a variable ui. This ui variable is some kind of a look like very score function, and its properties will be approximate to the likelihood. So that is why we were dealing with concerning a variable yi, and yi is equal to yi minus expectation of yi divided by variance of yi. So it's kind of a standardization, and we will put the values. Yi, expectation of yi is lambda, variance of yi is lambda as well. Now what we will do, we will use the quasi-likelihood. Quasi-likelihood defined as q lambda, which is the mean or the parameter, yi the observation, parameter given the observation, and it will be the integration observation yi up to the parameter, which is the lambda, yi minus c. We will use this thing inside this integration, but we doesn't include the lambda because we given the limits as a lambda, so that we can find out as a last product in lambda. So we will use another variable called t. You can use any other variable if you want. So t here, dt, and if you integrate this one, so we divide this first of all, yi lambda, we can yi divided by t minus t by t dt. Next, we see this yi is constant, so it can be outside of this integration. So yi integration yi lambda 1 by t, and integration, see, dt, it will be 1 dt. Okay, so here will be dt as well. yi and 1 by t, see, integration of 1 by x is equal to ln x, so it will be ln t, and the limits are yi and lambda, and minus, if we integrate 1, then we will get the t as a integration product, and the limits, sorry, here is the limits yi lambda, yi and lambda. We will put the limits here, yi ln lambda minus ln yi minus lambda minus, that will be plus yi. So if we multiply this, yi ln lambda minus yi ln yi minus lambda plus yi. So it's a final product that we are getting from here. See, this is for only one individual, but what is for the whole observations? Suppose this is for a variable y1. Now we will go for y1, y2 up to yn. Then what will happen? The quasi-likelihood parameter given the observation is equal to summation 1 to n, because there is n size, this quasi-likelihood yi. So when we apply this summation, what we will get? 1 to n, and it will be yi ln lambda, minus yi ln yi minus lambda plus yi. And after we will put the values, integration, you will get ln lambda minus summation yi minus summation yi ln yi minus n lambda plus summation yi. And now this is the final product of the quasi-likelihood q of parameter given observation yi. Now we will find out the genuine likelihood that we use in MLE. So how we will do that? Likelihood parameter given observations, it will the product 1 up to n f of here's yi lambda. This product 1 up to n e to the power minus lambda to the power. So this is the one PDF, lambda to the power yi factorial, and when just product you will apply here, e to the power minus lambda n, lambda to the power summation yi, and product will be 1 to n yi factorial. Yes, it is. Now for simplicity we use log likelihood lambda yi. What will be found here? Minus n lambda plus summation yi ln lambda minus summation ln yi factorial. Now we found our final products for quasi-likelihood and the likelihood, and if you compare this one and this two, what we will get? See, minus n lambda. Here is minus n lambda. There is a minus n lambda. Then there is a ln lambda yi. Ln lambda yi. See, there is ln lambda summation yi. So this part's matched, but there is a part, this one, that is not matching with this equation 2, and this one. These two parts, these three things not match with each other. If you notice that in this part there is no lambda, that means there is no parameter. Here also not parameter, lambda is not present here. There is also not any kind of a parameter, lambda is present here. So when you derive this will be constant, so it's not that big deal. So our major concerns are matched with each other. So we will now say that this quasi-likelihood will be approximate to the likelihood. Thank you very much.